How's it, guys? Welcome to another video. Today I'm going to be speaking about one of the coolest concepts I ever encountered throughout my time working with science, and that is something that I worked on a little bit last video, but I'm going to go into more detail today, and it's the conservation of energy. And for the guys who watched the last video, you'll remember that I said that the definition of the conservation of energy is that energy cannot be created nor destroyed, just transformed from one form to another. Okay, guys? And this applies to any form of energy that we have. Guys, remember, energies, if there's any form of movement, any form of power related with that thing, that has energy, guys. So something as simple as, I don't know, you closing a door, you are, what's it called? You are moving the energy from your body into the door, and then that door is being given the energy so that you can close it. Okay, so I'm just going to go through a few types of conversions so that you guys get an idea of what I'm talking about. The first one that I want to talk about is just light energy to heat energy, guys. It's one that you guys will all see every day. It's that light energy doesn't just dissipate into the air when it hits us, guys. Is that a lot of it has to be converted when it hits our Earth's surface. So a lot of it is converted into heat energy. This is one of the reasons why if you go have a pool day or something like that, your skin starts to get very hot. It's because that's actually the light energy being converted into heat energy. Another thing that light energy can be converted into chemical potential energy. This is for my bio kids, is that light energy is converted into energy in the through photosynthesis, guys. Like, it might not seem like a very sciencey, type of energy conversion, but it's actually a very important one. It follows the exact same rules. The same amount of energy that is being absorbed from the sun is being put in out as chemical potential energy in our food, guys. And then lastly, the one that I really want to speak to you guys about, because it's the one that comes up mostly in your guys' syllabus, is gravitational energy and kinetic energy. The two of them freely, guys, like very freely, they convert to each other like it's nothing, guys. Is that because when you lift something high in the air, you are giving it gravitational potential energy. If you were to stop giving a force to that, holding it in the air, that thing would just drop to the floor because the gravitational energy has to be converted into something. And in this situation, it's kinetic energy. So let's go look at an example so that we can get into some problems so that you can see how you use it. So let's look at this. Okay, so we have our skateboarder going on his half pipe. You see at point 1, he's 2 meters above the top of the ramp, which is actually, as you can see on the side, it's 10 meters in the air. And you can see that he has a mass of 80 kilograms, guys. And you see that he goes up there, and then as he falls, he slides, and then he goes all the way to point 2. Okay, guys, now the thing that I wrote down here, E1 is equal to E2. This is due to this definition we said here, the conservation of energy. Energy cannot be created or destroyed. So that means is that no matter where the skater is on this ramp after he starts falling, the energy he has at point 1 will be equal to the energy at any point he has along the ramp. But for this situation, we're just going to call it point 2. So we know that the energy he has at point 1 is equal to the energy he has at point 2. And now we're going to assume that this is done in a vacuum and things like air resistance and friction are taken out of account, because that does change your equation, and that's where energy loss comes into play. But for the science that we do under matric level is that we don't take that stuff into account, and we just look that energy is completely conserved, so the energy at the top will be equal to the energy at point 2. So now let's go into the thing. So if E1 is equal to E2, it means that gravitational energy at point 1 plus the kinetic energy at point 1 is equal to the gravitational energy at point 2 and equal to the gravitational energy, at the kinetic energy at point 2. So what we can do is that now we write out that formula in terms of our symbols. So it's mgh, so mass times gravitational constant times height. Okay, so that is the formula for gravitational energy, guys. And then we've already done this. The formula for kinetic energy is half times mass times velocity squared. Okay, now we can put our values into it. So we put for the point 1, he's 80 kilograms. Okay, you times the gravitational constant, 9.8, and as we can see, he is 10 meters above the ground. So we put a 10 there. If that is the max height that he reaches when he's skating on this thing, we know when he is at the max height, when we did our equations of velocity, at the max height, that is where his velocity is 0, because he is turning around. Is that he's accelerated up to the top, and now that is the point where he is turning around. So he has a velocity of 0. Then the other side, so now we're looking at point 2. He has, this guy is 8 meters above the ground because he's at the top of the ramp, and the whole thing is 10 meters. So we know that the ramp is 8 meters. So we go 80 times 9.8 times 8 plus half times 80, but we don't know what his velocity is here, guys. So we have to leave v squared as it is, okay? So then just through some normal reshuffling of the equation, we get v is equal to the square root of 80 times 9.8 times 10, so the gravitational energy at point 1 minus the gravitational energy at point 2 over 40 because of the half times the 80, guys. So I just skipped a few steps because you guys can do the math yourselves. And then after that, you will get a velocity of 6.26 meters per second, guys. So then you can plug it into your original formula to see if the two sides are equal. But if he is traveling at a velocity of 6.26 meters, then energy is conserved, and that will be the velocity he's moving at along this ramp. Okay, guys? So that's a very simple concept, right, guys? We're just taking the energy is completely conserved, so we know he has to be moving at that velocity just due to this equation. But now I want to bring up another concept, guys, and it's about the fact that everything in science is relative, guys. If you set parameters and rules before you make the sum, you guys cannot go wrong. So I'm going to just give you an example here on how you would set parameters. Because remember, in science, we work with vectors and scalars, guys. These things are all vectors here, guys. So even the height, guys, the height is the most important one. The height is a vector, guys. So if you, what's it called? Dictate the starting point, okay? So so it doesn't have to be your starting point, the ground. If you dictate the starting point as the height of the ramp, then that is your starting point, and then it shouldn't affect your equation. So let's look at that. So we're going to say point 1, he's only 2 meters along there. So we're going to say point where h is equal to 0 is the top of the ramp. So where this guy is at point 2. Okay, so now we're going to redo the equation the same way that we did last time. So we go to point 1. We have 80 times 9.8, but now we times it by 2 because he's only 2 meters above h0, only 2 meters above the ramp. We plus 0 because his kinetic energy will be 0, because at that point he's stationary, he's turning around, he's about to start moving towards the earth again, is equal to 0 because, guys, so this is the gravitational energy at point 2. Because we have said, what's it called? The top of the ramp is where h is equal to 0. The gravitational energy is therefore equal to 0. And then we do the same thing, half times 80, so his mass, v squared. Okay, guys, so once again, I'm not going to go through the full effort of reshuffling it. I'm just going to take you to this step. So now from that, we get v is equal to the square root of the gravitational energy at the top, so 80 times 9.8 times 2 over 40. And then we get our v is equal to 6.26, which is the exact same answer we got earlier, guys. So that was just to show you basically how, guys, if you guys set rules and parameters to yourself before you start, so it works with stuff like equations of velocity. If you set up as your positive direction, then you have to stick to that rule throughout, is that up has to stay positive. If the guy's moving down, it has to be minus, okay, guys? It's just important to remember that, is that when we're doing these type of sums, as long as you set a good starting point, your equation cannot be wrong. And as long as you keep to that starting point, your equation cannot be wrong. Okay, guys, thanks for listening in. Sorry it was a bit of a long video, but I hope this could have been of some help to pass your guys' exams this year. Thanks a lot. Cheers.